Hello and welcome to lecture 20 on numerical root finding. All right, so in this class we focused a lot on finding the roots of different functions. And so in this lecture we're going to talk about how to find the roots of those functions using a computer. So in the previous lecture we talked about algorithms and how to find the maxima or minima of functions using algorithms. In this lecture we're going to extend that to talk about how to find the roots of a function using algorithms. All right. So, just as a review of roots of functions, what is the root of a function? A root of a function f of x is the values of x. So they're the special values of x such that f of x star is equal to 0. So we're trying to find the x star such that f of x star is equal to 0. These correspond to places where you have changes in the sign of f of x. So if you're crossing the x-axis, you go from either being negative to positive or positive to negative. All right, so we have several biological functions. The first of them is a polynomial. If we have a line f of x, which equals mx plus b, which is a first degree polynomial, this has at most how many roots? It has at most one root, and that root occurs at minus b over m. All right, the quadratic function, the second degree polynomial, has at most how many roots? It has at most 2 roots and in its domain, and these are at the points x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. All right, if we have a higher order polynomial, so an nth degree polynomial, it has how many roots? It has at most n roots. And if n is greater than or equal to 3, these roots can only be easily found or only be found if the polynomial can be factored. All right, we did an example where we factored a polynomial to find the maxima and minima in one of the previous lectures. So check that out if you need it. All right, so we have other functions. We have the roots of logarithms. So suppose we have the log base b of x. This has how many roots and at what value? It has at most one root, and a logarithm looks something like this, and it intersects the axis like this. And so if we're trying to figure out when the log base b of x is equal to 0, what we're saying we can solve for x. We have b to the 0th equals x. What is b to the 0th? It's 1. So the root here is at 1. X star equals 1. So independent of what b is, it doesn't matter what b is, you have a root at 1. What about an exponential function with base b? Well, we know that exponential functions either grow or they decay, and they get closer or further away from 0, but they never cross 0, so they have 0 roots. All right, so those are the roots of biological functions, and in the case where you have a higher order polynomial, you may or may not be able to solve for those roots mathematically. So suppose that you have a higher order polynomial, some complicated function, and you want to find the roots. How do we find the roots of those functions? Well, we can use a computer and the Newton-Raphson algorithm. So we talked about algorithms in the previous lecture. So if you need to go back and review the steps of an algorithm, please do that. And we're going to use tangent lines and the help of derivatives to find the roots of a function. So the first thing that we want to do is we want to randomly guess. So say pick a random x0. So this is a random guess for our root. So we start by guessing the root. All right, suppose we have some crazy function, some crazy higher order polynomial. Let me sketch one just as an example. Something like that. So some crazy function. And suppose we guess our initial x0 as being right there. Okay, so we just pick a random guess. Then in the first step, what we're going to do is graphically, we're going to draw the tangent line to this curve. Suppose we have the tangent line, and then we're going to say our new guess, our x1, is the place where this tangent line intersects the axis. So it's the root of the tangent line. All right, so we know how to find a tangent line. The tangent line is t0 of x0, is going to be the intercept of the tangent line. Remember what the equation of the intercept of a tangent line is? It's the value of the function minus how far you've got to go to get to the axis times the slope. That's the intercept. And then we have the slope of the function at that tangent line, which is by definition the derivative, times the independent variable. All right, and we're going to set this equal to 0, and we're going to solve for x. We're going to find the root of our tangent line. All right, moving this over to the other side of the equation, we have that f prime of x, 0 times x, is equal to x0 f prime of x, 0 minus f of x, 0. Now we're going to divide by f prime of x0. That goes away, that goes away. We're going to divide by f prime of x0, and we get that x1, our root of our tangent line, which is our new guess, is going to be the old guess minus f of x0 divided by f prime of x0. So this is the algorithm that we're going to use throughout, that the new guess, the next step is the previous step minus this ratio. All right, so what does that give us in our plot? That gives us this new guess here. All right, now we're going to repeat that over and over and over again for xi equals I equals 1, 2, up to n. And so for each step, you get the next guess by solving for the tangent line at the old point for the intercept, or the root of the tangent line. So let's do that here. We have our new guess here. Let's draw the tangent line there. All right, where does this have a root? It has a root there. Okay, this is our value of x1. All right, so now we want to take x1 and we want to say, what is the tangent line at x1? The tangent line at x1 comes way out here. Actually, let's just redo this just a little bit. So things like that can happen. Let's just redraw this tangent line just a little bit to make our drawing simpler. Okay, so here's our new root. Here's x2. All right, so this has our root here. Now, let's draw the tangent line there. And we draw the tangent line like this, and the tangent line comes out to being here. So x3. All right, now as you can see, this value of x3 is really close to what we had before. All right, so in general, we have the tangent line at point I of xi is equal to, well, you know the equation of the tangent line, f of xi minus xi f of xi plus our independent variable f prime of xi, the slope. All right, if we solve this, we get xi plus 1, our new guess, is equal to our old guess minus f of xi divided by f prime of xi. And we're going to repeat this over and over and over again until we get xn. So once we get xn, how good have we done? Is our root estimate. How good is xn at estimating the root? Well, we don't know the true root, but we know that at the true root, f of x star, that the function should equal 0. So what we really want to know is if we plug xn in, is this approximately equal to 0? How close is our guess to being a root of the function? All right, let's see how this plays out with an actual polynomial. For example, the polynomial x squared minus 2x, or x cubed minus 2x squared minus 5x plus 6. So I've drawn this cubic polynomial over here. What is the derivative of this cubic polynomial? We're going to need that to use the Newton-Raphson method. That is equal to 3x squared minus 4x minus 5. All right, if you need to pause the video to figure out what that derivative is, please do so. Well, it turns out that this is a special cubic polynomial that we can actually factor. So we can actually find the exact roots. We'll then use a Newton-Raphson method to see how good we do. All right, so let's find the actual roots. Well, we could factor this polynomial to be x plus 3, x minus 2, and x minus 1. All right, so if we do that, then we have these three roots. We have a minus 3, we have a plus 2, and we have a plus 1. All right, so let's draw those over here. We have this one here, and this one there. So yes, those are indeed the roots of this polynomial. All right, now let's use the Newton-Raphson method. So suppose we didn't know how to factor that polynomial. Let's use the Newton-Raphson method, and let's iterate it 2 times, starting at x equals 3, to see how close we get to our estimate of the root. All right, so let's start at x0 is equal to 3. Okay, so where are we on here? We're at 3, so we're going to go there, and we're going to find the tangent line to this curve, and we're going to ask, what is the root of that tangent line? So f of x0 is equal to 12, and f prime of x0 is equal to 20. All right, so if we have those two, then we want to calculate x1 is equal to x0 minus f of x0 divided by f prime of x0. So if we do that, we have the original guess, which is 3, minus the value of the function divided by the slope, and this comes out to being 2.4. So we move over to 2.4. So it's about there. All right, let's do this again. We go up, and we're going to take the tangent line. This is getting really hard to see, really tiny, but let's do this anyway. Okay, so if we have f of 2.4 is equal to 3.02, and f prime of 2.4 is equal to 10.3. So our new guess, x1, is the old guess, 2.4, minus 3.02 divided by 10.3, which comes out to being 2.105. All right, so how good of a job do we do? Well, in this case, we know that there's a root at 2, so we do a pretty good job of finding that root at 2. But how good we do as far as the value of f? Well, if we plug in 2.105 in here, we get 0.6. And so, yeah, this is reasonably close to 0. It's not very close to 0, but relative to where we started at f of x equals 0 equals 12, it's a lot closer to 0. So we've done a fairly good job of getting the root. Okay, what if we started somewhere else? What if we started at x equals 0? Suppose x0 is equal to 0 instead of 2. So in this case, we're starting as our initial guess there. All right, and then we're going to draw the tangent line here. And we're going to ask, where does it intersect? All right, so I'm going to start at x0 equals 0. And then I have f of x0 is equal to 6. And f prime of x0 is equal to minus 5. So I have x1 is equal to the initial guess of 0 minus 6 divided by minus 5, which comes out to being 1.5. Notice that the minus signs cancel there. All right, so, 1.2. 1.2. All right, so now in order to calculate the next step, we need to figure out what f of 1.2 is. If I evaluate this, I get minus 1.15, and f prime of 1.2 is equal to minus 5.48. So then we end up with x2 is the x1 value, which is our previous guess of 1.2, minus 1.15 divided by minus 5.48, plus those cancel. All right, so we ended up overstepping our root, and now we're going backwards just a little bit, and we get x2 is equal to 0.98. Now, this is a special case where we actually know the true roots, and so we got really close to finding that root there. We're really close to it. So we're at 0.98 instead of 1. All right, but how good do we do as far as f goes? Well, if I calculate f of 0.98, I end up having I don't actually have the value here, sorry, I did 3, but it comes out to being something like 0.01, so it's very, very close to the true root. All right, the thing that I really wanted you to notice here is that if we started over here at a value of 3, then we come really close to finding the root at 2. If we start at 0, we come really close to finding the root at 1. So where you start can change which root you find. So which root you find depends on where you start. So if a function has more than one root, then where you go ends up depending on where you start. So if you want to find a root, you might want to try a specific root. You might want to try starting in multiple different places. All right, so let's compare our answers to A, B, and C. Well, we have the true roots of -3, +2, and +1. We never ever estimated something that started over at -3. To do that, we might want to actually start with the initial value of x over at -5 or something like that. All right, but when we did do our guesses, we started at 3 and we came really close to finding the root at 2. And when we started at 0, we came really close to finding the root at 1. All right, so with that, I'm going to let you use the Newton-Raphson method to find the roots of another polynomial.